Okay, Integrated Math 3 fans, our topic for today, this is in Module 11, 11-1, 11-2, simplify radical expressions and using rational exponents as well. Before we begin, let me give you your joke of the day. What do snowmen call their offspring? And the answer is children. All right, so our goal for today is to simplify expressions involving rational exponents, that's fraction exponents, as well as radicals. And radicals would be anything with this symbol. That would be a square root. This would be a cube root, fourth root, and so on, okay? This number here is the index for that. Now, if there's no number there, that's automatically a 2. That's what we call the square root. We don't put the 2 in there, but we will for cube roots, fourth roots, and so on. Now, before we actually start these notes, we're going to take a look at something that I call a power card. Now, power is just another word for exponents. And so what you have here, if you look at the first column on the left, these are the x values from 1 to 15. And then the second column here, this is x raised to the second power. So when we square, when we raise it to the second power, that means we take the number and we multiply it by itself. So if we take 2 squared, for example, that is 2 times 2, which is how we get to 4. 9 is 3 times 3, 16 is 4 times 4, and so on. And so here's the first 15, what we call perfect squares. And then next to that, we have what we call the perfect cubes. Now this would be from 1 to 10. These are the perfect cubes. So for example, if we take 2 raised to the third power, that's not 2 times 3, that means 2 times 2 times 2, which is how we get 8. 3 cubed, 3 to the third is 27, 4 cubed is 64, 5 cubed is 125. Okay, and we can keep going. So if I asked you, for example, what is 5 raised to the fourth power, if you're using this power card, we would find the x value, which is 5, and then we would go over to x to the fourth, and where they meet is 625. So you can do exponential arithmetic very quickly using this. Of course, you can use, a calculator as well. So if I did 5 raised to the fourth, then there's my 625. Okay, so I can also use that. Now, it is a good idea because we deal with exponents quite a bit. It's going to be faster for you if you memorize these. Now, I would say for perfect squares, you definitely want to memorize all 15 of these. You already know the first 10. I mean, that's from your times tables going back to elementary school. Now, for the perfect cubes, I would say definitely up through the first 5. Because again, you're going to see these numbers quite a bit. Now, after that, to the fourth, to the fifth, to the sixth, if you can memorize them, it just makes the work faster for you. Now, the other thing is, so we can do exponential arithmetic, but we can also do what we call radical arithmetic. And radicals, like I said before, are kind of like square roots and things like that. If I ask you the square root of 144, now we know it would be in the x squared column. So now we're working backwards. So here's 144. The square root would be the x number where we started from, and that was 12, because we had 12 times 12 is 144. If I asked you for the fifth root of 243, we would go to x to the fifth, find 243, which is here, and then come over. What was the x value? Oh, it was 3. The fifth root of 243 is 3. And again, a radical is just going to undo an exponent. So if I say 3 raised to the fifth is 243, I can undo that by saying the fifth root of 243 gets us back to the original number, which is 3. Okay, so exponents and radicals are related to each other. They are inverse operations. So when we look at, so here's our definition, the nth root of a, this is how we read it, the nth root of a, where we're not sure what this number is right here, but it could be anything. It could be square root, it could be cube root, it could be fourth root. The way that we think about this, if we have some number b raised to an exponent and it gives us a value a, then it means that the number for b, the value, is equal to the nth root of a. So again, these are inverse operations. They're saying the same thing, but just from a different direction. Inverse operations. So if 5 raised to the second is equal to 25, then we can say that 5 equals the square root of 25. So here's the square root. 6 raised to the third is 216. Well, that means that 6, which is the base, is equal to the third root or the cube root of 216. If some number raised to the fourth is 256, then we can say that x is equal to the fourth root of 256. And if we use our power card, you will see that that is equal to 4. Okay, so looking at exponents or powers, one other thing to think about, the bottom value, when you're looking at an exponential expression, this number here, in this case the variable, is what we call the base, and then here is our exponent or power. Okay? All right, so let's look at some examples here. Directions. Simplify the following radical expressions. Now, simplify can also mean to evaluate if we can come up with a value, like a number from it. The cube root of 343. So let me have my power card handy here. The cube root, so I'm going to look at the perfect cubes. 343 is right there, and that's equal to 7. So again, you can use a calculator for this. In these cases, I'm going to use the power card and try to do them in my head. The fifth root of negative 32. Now, we cannot take the square root of a negative number. If you try to do that, and just to show you on the calculator, square root of negative 9, it tells me there's an error. It's a non-real answer. So we can't take the square root of a negative because remember that when you do a square root, you're thinking of something times the same thing that gives you this. So we can't say it's 3 because 3 times 3 is positive 9. But we can't say it's negative 3 because a negative times a negative is also a positive. So there's no number times itself that gives us negative 9. So it is non-real. Now there actually is a way to simplify that. We'd have to deal with something called an imaginary number. But that will come up at a different time. But we can take the fifth root of negative 32. Because if you do a negative times itself an odd number of times, you do end up with a negative. So fifth root, let's go to x to the fifth. Oh, there's 32. The fifth root of positive 32 is 2. So the fifth root of negative 32 is negative 2. And again, I like to check my answers. So if you're not sure, if you do negative 2 raised to the fifth, and notice how I put that in parentheses, there's my negative 32. Now number 6, the square root of 324. Now that is not on the power card, but that is equal to 18. The cube root of 27 is 3. And now we can simplify that. 18 divided by 3 is 6. Now if you take the cube root of an overall fraction, that's fine. That's the same thing as doing the cube root, though, of the numerator divided by the cube root of the denominator. And that would be negative 5 over 4. Now as a fraction, we always want to simplify, but in this case, it's good. All right, so what happens now if we have variables? Well, we're thinking of something times something that would give us x to the 8th. These have to be the same thing. And in this case, it would be x to the 4th times x to the 4th. So the square root of x to the 8th, now you don't need to do this step here. It would be x to the 4th. The 4th root of x to the 8th. So now we're trying to think of 4 things that would multiply by itself that would get us to x to the 8th. Now, one of the other things we need to understand is our rules for multiplying with variables. If I take x to the 2nd times x to the 3rd, the rule is we add the exponents. So when I'm trying to think of 4 things here that multiply that would give me x to the 8th, I would be adding up these exponents, and so those would be x to the 2nd. Because if I add the exponents, 2 plus 2 plus 2 plus 2 is 8. Now what you start to realize here is that there's a pattern to this, the 5th root of x to the 15th. I'm thinking of 5 values that are the same that would get me x to the 15th. Well, if I take 15 divided by 5, because I need 5 groups here, I would get x to the 3rd. And then the square root of x squared. Now we've actually done this quite a bit. When we do Pythagorean theorem and we end up with a situation like x squared equals 25, we take the square root of both sides, and what we get is x equals, and in this case that would be 5 for that. The square root of x squared is equal to x. However, we do need to be careful here, because if I take the square root of 25, there's actually 2 answers to this. It's 5, but it's also negative 5. The square root of this number, I could do a negative times a negative, and I would still end up with 25. Now, why have we not done that before? Well, when we do Pythagorean theorem, what happens is we're looking for the length of a triangle, and a length can only be a positive number. Distance is positive, so we ignore the negative. However, if we're solving this equation, technically there's 2 answers, x equals 5 and x equals negative 5. Now, when we're evaluating with a square root, we're only going to use the positive value for that if we're evaluating this. If we're solving an equation, it's different. For this, the square root of 25 is always going to be 5. The square root of x squared, though, is actually equal to the absolute value of x. Since we need this to end up as a positive value, we're going to use the absolute value because, again, if x was negative, if this was negative 5, the square root of negative 5 squared, it would still give us positive 5. It wouldn't give us negative 5 for that. And that is the end of part 1.